So in today's video, we are going to be talking about something called trigonometric identities. And in a few minutes, I will explain what the word identity means in this context. But kind of big picture, the thing that is going to be different about this section compared to earlier sections that we did is we're no longer going to be taking sine and cosine and tangent and all the trig functions and plugging in numbers into them. We're not going to really be evaluating trig functions. We're more going to be treating them as algebraic expressions and seeing how we can take one expression involving different trig functions and rewrite it in a simpler way. So a lot of this is going to be kind of similar to what you would do in like an algebra class when you learn how to combine like terms or multiply two things together, things like that, how you can kind of go from one algebraic expression to another one that's equivalent. So that's kind of big picture what you should expect in this section. So first thing I want to talk about, like I just said, is what does it mean when we say an identity? So what is an identity? So it's a word you might have seen come up in a math class before. But this is probably the first time you'll really be working with identities a lot. So what is an identity? It's basically an equation. So an identity is an equation, but it's not an equation that you solve. And it's an equation that is true for all values of its variables. So it's basically like a true statement. And so I'll give you some examples in a moment. But basically, why are identities useful? Basically, they're often used, so identities are often used to either simplify expressions. Identities are often used to simplify algebraic expressions, or maybe like sometimes it's not even necessarily simplifying them, but just kind of rewriting them in a different but equivalent way. So I want to give an example of an identity that has nothing to do with trigonometry, and then we'll see what they look like in the context of trigonometry. So an example of an identity would be x plus y squared is equal to x squared plus 2xy plus y squared. Right, because that's what you would get if you took x plus y and you multiplied it all out, you would get x squared plus 2xy plus y squared. And so the left-hand side and the right-hand side are completely equivalent to each other, right? Like if you were to pick any numbers you want for x and y and plug them in on the left side and plug them in on the right side, you'll get the same thing because the left and the right-hand side are just equivalent to each other. So what's an example of something that is not an identity, that's something that's an equation but not an identity? That would be something like x squared plus 1 is equal to 10. That's an equation. So there are numbers that would make this true, right? If you were to plug in x is equal to 3 or x is equal to -3, then this would be a true statement. But it's not true for all values of x, right? If you plugged in like x is equal to 1, you would get 2 is equal to 10, which is not true. So it's not an identity. So now getting into trigonometry, and we'll see a whole bunch more examples in a second, but just to show you a couple. So one example of a trigonometric identity would be that secant of x is equal to 1 over cosine of x, right? Because that's like the definition of secant. Secant is defined to be the reciprocal of cosine. So it's definitely true that no matter what angle you plug in for x, it's always going to be true that secant of the angle is equal to 1 over cosine. And another example of something that's not an identity would be something like cosine of x is equal to 1. That's an equation and it has some values that work, right? So for example, what would be an example? 0. When you plug in 0 for x, cosine of 0 is 1. However, if you plug in like pi or pi over 2 or pi over 4, like lots of other different angles, this is no longer true. So it's not an identity. Okay, so I want to go through, so maybe let me actually open a new page here. So we're going to start with one kind of variety of identity and then do some examples working with those. And then we'll also talk about another type of identity and do some examples working with that second type. So the first type I want to talk about are basically rewriting every trig function in terms of sine and cosine, expressing in terms of sine and cosine. So we'll see that these, they almost seem like they're not really identities because there's something that we already know. They're just kind of using the definition of the trig functions, but these are going to be really, really useful in simplifying, and we'll see why in a couple of minutes. So what do I mean by expressing in terms of sine and cosine? Well, for example, if you wanted to talk about cosecant of theta, that is the same as 1 over sine of theta. Or if you want to talk about secant of theta, we know that that's the same as 1 over cosine of theta. We've also talked about how tangent of theta can be written as sine of theta over cosine of theta. And that one maybe isn't quite as much of like the definition, but where does that come from? Well, if you think about it on the unit circle, tangent is supposed to be the y coordinate over the x coordinate, sine is the y coordinate, cosine is the x coordinate. And then the last one is that cotangent of theta, so that's supposed to be the reciprocal of tangent, and so that's going to be cosine of theta over sine of theta. So let's see how we can actually make use of these. And by the way, in this section, we will be using different input variables, just like kind of mixing it up. So sometimes you'll see theta, sometimes you'll see x, sometimes you'll see t. We might use a different letter. It doesn't really matter. It all just represents, any angle, basically. Okay, so let's do some examples. We'll see that basically just by using those definitions, those ways of rewriting things in terms of sine and cosine, that can go a really long way in taking an expression and making it look a lot simpler. So first example, let's do secant of t. So we're going to simplify the expression secant of t times sine of t. So basically all we want to do is rewrite these in terms, so sine is already in terms of sine and cosine, so there's nothing to do there, but we can take secant and rewrite that as, so let me just copy this down. So secant of t times sine of t is equal to, so we can rewrite secant of t as 1 over cosine of t, and then we're multiplying that with sine of t. So if you multiply these two things together, you get sine of t over cosine of t, which we know is equal to tangent of t. So we started with the product of two different trig functions, but at the end of the day, we realized that we could actually just write it as one trig function. So that's how most of these examples are going to go. It's like we're going to kind of start by breaking everything down, writing it in terms of sine and cosine, kind of see what can combine. In some cases, some stuff will cancel out. And then at the end, we'll rewrite it in terms of a single trig function if possible. And so that's what it really means by simplify is, if you can take something that is a product or a quotient of two different trig functions and get it to just be one trig function, then that's a simpler way of writing it. Okay, so let's do another one. So let's do sine of theta. So we're going to simplify sine of theta times cosecant of theta. So again, so sine of theta is already written in terms of sine of theta, but then we want to take cosecant and rewrite it as 1 over sine of theta. So what happens when we multiply these ones together? Well, we get sine of theta over sine of theta, which is just equal to 1. And so that kind of makes sense if you think about it. When you take something, some number and its reciprocal and multiply them together, you should get 1. And cosecant is defined to be the reciprocal of sine. So it shouldn't be too surprising that you end up with 1. Okay, let's do a couple where we're now dividing. So let's do sine, or let's start with this one. Let's start with cotangent of theta divided by cosecant of theta. And sorry, I should have said, I just want to be consistent here. So I'll say simplify cotangent over cosecant. Okay, so we want to rewrite each of these in terms of sine and cosine. And in this case, we're going to end up with a fraction over a fraction. So we're going to have to make use of what we know about dividing fractions. So cotangent, that's a reciprocal of tangent. And so that can be written as cosine of theta over sine of theta. And then the next one, or the denominator, is cosecant. So that one we already saw, that's a reciprocal of sine. So that's 1 over sine of theta. So how do you simplify something that looks like this? Well, when you're dividing by a fraction, that's the same thing as multiplying by the reciprocal of the fraction. So we can rewrite this as cosine of theta over sine of theta times sine of theta over 1. And so in this case, we can see that these sine of thetas are going to cancel out, right? Because if we were to multiply all this together, we would have cosine times sine over sine. And so the signs are going to cancel each other out. And so what we're left with is cosine of theta over 1, or just cosine of theta. So again, we started with something that was a division of two functions, which aren't really the first kind of simple trig functions, right? They're like the reciprocal functions, but it turned out that once we simplified, it was actually just cosine. All right, we'll do one more with using these types of identities. Okay, so next one, let's do sine of theta, or I'll say sine of x. Let's mix up the variables, over cosecant of x. So again, we want to rewrite, in this case, we have sine of x in the numerator, so that is just going to stay as it is, but in the denominator, we know that cosecant can be written as 1 over sine. And then dividing is the same as multiplying by the reciprocal. So dividing by 1 over sine of x is the same thing as multiplying by sine of x over 1. And so if we multiply these two together, we get sine squared of x. So there will be some examples where when you do the simplification, you don't end up with just one single trig function, but still, I think in a lot of ways, sine squared of x is kind of a nicer, more simple expression than saying sine of x over cosecant of x. Just to quickly remind you again, because this hasn't come up for a little bit, but so this notation of putting sine squared of x, so just a reminder, if you have any trig function, so I'll just do sine, but it's true for any of them, if you write down sine of x squared, so sine of x times sine of x, a kind of nicer way that we're going to be writing that is to write it as sine squared of x. So it's really just a notational thing. It's just another way of saying, take this whole thing and square it. It just helps you kind of avoid any confusion about what part is getting squared, whether it's the input that's getting squared or the whole thing. Okay, so now we're going to do some examples with some other, or first we're going to talk about some other trig identities, and then we will do some examples using those identities. So these next identities, and there's going to be 3 of them, are called Pythagorean identities. So the first one is one that we have talked about before. And this one, so we'll see actually that really the one we're about to write down is really the only one you actually have to remember, because the other ones, once you know the first one, you can kind of get them from that first one. So the first one is that sine squared of theta plus cosine squared of theta is equal to 1. So quick reminder, where does that come from? It basically just comes from the unit circle equation and the definition of sine and cosine. So if you go to an angle theta, so let's say this is our angle theta, we have a point where the x coordinate is cosine of theta and the y coordinate is sine of theta. And so we know that the equation of the unit circle is that any point that lies on the unit circle has to satisfy x squared plus y squared is equal to 1. So the x coordinate of this point is equal to cosine, so we get cosine squared theta. The y coordinate of this point is equal to sine, so we get sine squared theta is equal to 1. So that's where the Pythagorean identity, the first one, comes from. It's just from basically the unit circle equation and the fact that the x coordinate and y coordinate are cosine and sine. Okay, so the other two you can actually get from this one just by going through and dividing everything by a different trig function. So I'm going to maybe kind of do that below, and then we'll come back and write them down so that they're kind of all in the same place together. So if you wanted to, so I'll just say it this way, I'll say deriving. So the word derive basically means that if you kind of have one identity or one formula and you kind of manipulate it to come up with another formula, that is called deriving a formula. So we're going to derive the other two Pythagorean identities. So what we're going to do is we're going to take this, this first equation that we had. So we had sine squared of theta plus cosine squared of theta is equal to 1. So the first thing we're going to do is we're going to divide everything in this identity by sine squared. So divide by sine squared of theta. Because when you have an identity, it's an equation that is always true, right? We're saying the left and the right-hand side are equal. And then anytime you have an equation, you're allowed to do the same thing to both sides of the equation, right? So we're just kind of taking this equation and turning it into a new one. So if we go through and we divide everything by sine squared, if we then simplify everything, so what is sine squared over sine squared? That is 1. What is cosine squared of theta over sine squared of theta? Well, cosine over sine is cotangent, and so this is going to be cotangent squared of theta. And then what is 1 over sine squared? Well, we know that 1 over sine is cosecant, so 1 over sine squared is going to be cosecant squared of theta. So we can add that to our list up here. So 1 plus cotangent squared of theta is equal to cosecant squared of theta. And personally, I don't really spend brain space on memorizing that second one. Like truly, if I ever, and we'll see some examples in a moment where we'll actually make use of these, if I kind of recognize something where I'm like, oh, I probably have to use one of those other Pythagorean identities, I will literally write down this one because I'll never forget this one. And I'll just go through and divide it to get the other ones because it's just, otherwise you just might remember them wrong. So I think just memorizing that first one, and then when the time comes to use them, just write down the other two and go from there. Okay, so how do we get the second other one? Well, similarly, we take our original equation and we divide everything now by cosine squared and see what that gives us. So the original equation again was sine squared of theta plus cosine squared of theta is equal to 1. So if we go through and we divide everything in there by cosine squared of theta, that will give us another true statement. So sine squared of theta over cosine squared of theta, we know that sine over cosine is tangent, and so that means that sine squared over cosine squared is tangent squared of theta. And then what is cosine squared over cosine squared? That's just 1. And then 1 over cosine squared, that is equal to secant squared of theta. So we can add that one to our list as well. Tangent squared of theta plus 1 is equal to secant squared. Okay, so one other thing to kind of say is that once you have these, you can get other identities from them as well. So, and we'll see how that comes up in a little bit, but just to kind of give an example, another identity that could come out of this, let's say that you decided to subtract sine squared from both sides of our original identity. So if you subtract sine squared from both sides, you would get cosine squared of theta is equal to 1 minus sine squared of theta. Or you could subtract cosine squared from both sides and you'd get sine squared of theta is equal to 1 minus cosine squared of theta. So my point is just that all of these equations, they're kind of like, you can think of them as your kind of starting point, and then depending on what you encounter in the actual expression you're trying to simplify, you can kind of rearrange things to suit your needs. And we'll see what that looks like in a moment. Okay, so let's see some examples using this type of simplification. So the first one again was sine squared of theta plus cosine squared of theta is equal to 1. Next one we got by dividing everything by sine squared, so that gives us 1 plus cotangent squared of theta is equal to cosecant squared of theta. And then the third one we got by dividing everything by cosine squared of theta, so that's tangent squared of theta plus 1 is equal to secant squared of theta. Okay, so let's look at some examples. So first one, we are going to simplify, and I kind of actually gave this one away accidentally on the last page, but I'll just do it again. So we're going to simplify the expression 1 minus sine squared of x. So this is kind of what I was talking about on the last page, which is if you have an expression that like kind of reminds you of something related to the Pythagorean identities, basically if you have a sine or a trig function squared and then you're adding or subtracting and there's either another trig function or there's a 1, basically seeing those kind of pieces should clue you in, okay, I'm supposed to use a Pythagorean identity here. So in this case, we would want to look at this top one because we have sine and we have 1 and say, well, if this first equation is true, then it should also be true that if we subtract sine squared from both sides, we get cosine squared of theta is equal to 1 minus sine squared of theta. And so that tells us that 1 minus sine squared of theta is the same thing as cosine squared of theta. So that is our simplified version. Okay, so let's try another one. So let's say we wanted to simplify, 1 minus secant squared of theta. Or let's change the variable, I'll say x. So 1 minus secant squared of x. So again, if you see a trig function squared and you see a 1 and you're adding or subtracting stuff, that should clue you in that you want to look to your Pythagorean identities. And in this case, the bottom one is the one that matches with the functions that we're looking at, right? So in this case, we have to kind of look at these pieces and say, what could we do? How could we rearrange this equation so that we have 1 minus secant squared? So if we were to subtract, like for example, let's say you thought of subtracting 1 from both sides, then you would have secant squared minus 1, and that's not quite right. We want 1 minus secant squared. So in this case, it's going to take a little more rearranging. Let's subtract secant squared from both sides. So that will give us, if we subtract secant squared from both sides, we'll get tangent squared of theta minus secant squared of theta plus 1 is equal to 0, right? If we were to subtract secant squared from both sides. And then we can subtract tangent from both sides, right? Because negative secant squared plus 1, that's the same thing as 1 minus secant squared. So if we subtract tangent from both sides, we get 1 minus secant squared of theta is equal to negative tangent squared of theta. And so that tells us that our simplification is that 1 minus secant squared of x is equal to not just tangent squared, but negative tangent squared of x. So you definitely have to pay attention to the order that things are being subtracted, because that makes a difference. If you said positive tangent squared, that would be wrong, right? That's not the same as negative tangent squared. All right, another example. Let's do we're going to do, oops. So this one's going to bring in something a little bit different. We're going to simplify cotangent squared of theta minus cosecant squared of theta is in the denominator, and then the numerator is going to be tangent of theta. So this one is not just, straight up Pythagorean identity like the other ones, but we do have this denominator which should remind you of the Pythagorean identities. So in this case, we're going to have to figure out how to simplify the denominator, and then once we have an answer for that, we can kind of put it back in the context of the fraction and see what we get. So going back to these ones, so we're looking for, sorry to keep scrolling, we're looking for cotangent squared minus cosecant squared. And so that's going to be kind of like the one that we just did, right? Because we would need to subtract cosecant squared from both sides and then also subtract 1 from both sides. So if we were to do that, we would get cotangent squared of theta minus cosecant squared of theta is equal to negative 1, because we have to both, basically we're doing this, we're subtracting cosecant to that side, but we're also subtracting 1 to this side. And so they're both going to end up negative. So now that tells us that we can replace the denominator of this one with negative 1. So we have tangent of theta over cotangent squared of theta minus cosecant squared of theta. So we just figured out that the denominator is just equal to negative 1. And so that tells us that our expression is the same as negative tangent of theta. All right, we're going to do one more example. These, they're all kind of the same at the end of the day. So we'll do one more, and then I have a worksheet that has a bunch more examples, kind of like the ones that we've been doing. Really just all kind of making use of these identities in different ways. So our last example is going to be to simplify 1 minus cosine squared of t over cosine squared of t. So there's actually two different ways to do this, and I think I kind of want to do it both ways just to show you. So the easier way is basically the same way that we've been doing some of these other ones. So the easier way would just be to first focus on the numerator and say, that looks familiar, that looks like it might be related to a Pythagorean identity. So if we go up to our Pythagorean identities, we see that if we were to, so we have 1 minus cosine squared is what we have in our expression. And so I'll write that down here as well. If you were to take this and subtract cosine squared from both sides, we would get sine squared of theta is equal to 1 minus cosine squared of theta. So that tells us that where we have 1 minus cosine squared of theta, we can replace that with sine squared of theta. So let's write these both out. So the first method is we can just recognize that 1 minus cosine squared of t is equal to sine squared of t. So that gives us 1 minus cosine squared of t over cosine squared of t is equal to sine squared of t. So just replacing that numerator that we just figured out with its simplified version. And then what is sine squared of t over cosine squared of t? Well, we know that sine over cosine is tangent. And so sine squared over cosine squared, that's going to be equal to tangent squared. So that's probably the easier method. But I want to show you a second method because it's going to kind of relate to what we'll be talking about in tomorrow's video. And I think it's kind of a good warm-up for that. So the second method is to split this into two fractions. So anytime you have something, and I'll write this out here, anytime you have something of the form a plus b over c, that's always the same thing as a over c plus b over c. That's an identity in general about fractions, right? And I think the funny thing is that a lot of us, I think, are very accustomed to, if you see this, you know how to simplify it and get that. But I think we're less accustomed to having a fraction that's already combined like this and splitting it apart. But it's totally valid. Like there's no reason that you can't take a fraction and leaving the denominator the same, break apart the two parts of the numerator. And that's going to be a really important, that's, I think, a very, it's very underrated algebra trick. It comes up a lot in calculus. So definitely a good thing to keep in your mind. So how would that work here? Well, if we have 1 minus cosine squared of t over cosine squared of t, we can split that up into being 1 over cosine squared of t minus cosine squared of t over cosine squared of t. Right? We're leaving the denominator the same and just splitting it into two pieces. And then what is 1 over cosine squared? Well, 1 over cosine is secant. So 1 over cosine squared is secant squared of t. And then we have cosine squared over cosine squared, that's just 1. And so now if we look back at our identities, we know that, so if you were to take this equation and subtract, actually, let me make sure I'm getting this not backwards. Yeah, if you were to take this equation and subtract 1 from both sides, you would get secant squared, and I'll write that down as our last thing here. So if you subtract 1 from both sides, you get tangent squared of theta is equal to secant squared of theta minus 1. And so going back to what we have down here, our thing here simplified to secant squared of t minus 1, and so based on that identity, that's the same thing as tangent squared of t. So you can really think of these equations that we wrote at the top. Again, the first one is the very most important one, and then the other ones you can get from that first one, and then all this other stuff we wrote on the right-hand side, that's just taking these and kind of rearranging them to get them into the form that you need in the place where you actually are encountering them. So that's it for today, and tomorrow we'll do some more examples, getting a little bit more complicated, doing some other kind of algebra, and also, in the meantime, doing the same kind of stuff that we were doing today. All right, I will see you next time.